Science time. Today we are talking about linear motion. Linear motion. I want you to imagine. Let's do a little imagination game. Could you close your eyes so that I can tell you're imagining? I want you to imagine with your eyes closed. Yes, closed eyes. I want you to imagine that something is moving. Okay. How, in your imagination, you don't answer because this is your imagination and I don't actually care. How fast is that thing moving? And two questions. How do you know? And how would you measure that? Okay, so are you imagining something moving? How fast is that thing moving? Don't answer out loud. How do you know? And how fast is it moving? Okay, now open your eyes again. Pretty soon you're going to have your eyes closed again and again. You see this? It's not a magic trick. I mean, it's going to seem like a magic trick because it's really cool. But look at this. Look at this. Now close your eyes. And if you're watching this on YouTube, close your eyes. I have to trust you. Close your eyes. Close your eyes. Now look. Okay, now close them again. Close them again. Okay, now look.
That's crazy.
That's crazy. How can did this move?
How do you know? You just put it behind your back and switch hands.
Yeah, did this move? Yes or no? That's a yes or no question. Yes. How can you tell this moved? There you go. That's exactly it. Okay. Not in the same spot. I'm going to use that quote of Daxton's to go for the rest of the discussion. Not in the same spot. Okay. Now, so a lot of that was a joke, and I want you to, but not in the same spot is fundamentally what it means for something to be in motion. Right? That's what motion is not in the same spot. How do you know it moved? Well, because it's not in the same spot. But now, imagine, trying to think of how this could work in your imagination. If you're in outer space, imagine you're floating in outer space. You don't have to close your eyes for something, but imagine you're floating in outer space, and that same thing happened, except it wasn't me. It was just in a different spot. Like it just moved this far. Could you tell that it moved at all? Maybe not, because the thing that tells you that it moved, you had to. How do you know it moved? Where was it before? The marker, I mean, in that example. Where was the marker before? Yeah, it was from my perspective, it was on the right side, and then after I had you close your eyes, it was on the left side. Right? From your perspective, it's the other way around. But in essence, your reference point, you remember that vocab word, was me. Right? It was on this side of me, and then after you open your eyes, it was on this side of me. And without even realizing it, like not one single one of you thought in your head, oh, due to the reference point of Mr. Kimes' head, I can tell that marker moved. But without even realizing you did that, because you always have a reference point. Or what we sometimes call a frame of reference. Without getting too philosophical, this is true of your thoughts too. You always have a frame of reference in your thoughts. You've never had a thought in your head that wasn't filtered through the medium of your frame of reference, through the way you were raised, or the situations that you've been in. Your frame of reference determines everything. You can't tell motion in this physical science sense. You can't tell if there's motion except through a frame of reference. And in much the same way, you can't have thoughts except through your own frame of reference, your own frame of mind, we might say. If I were to say, your mom is in a car, this is your mom's car, obviously, polluting the atmosphere. This is your mom, their curly hair, their Karen haircut, looking like a mullet. This is no longer your mom. This is actually, I was going to say, it's Joe Dirt. That's much better. That's much better. I was going to say someone else, but then they died. So that wouldn't be good. I mean, death comes for all of us. So, but it was Toby Keith. Anyway, so this is Joe Dirt, and Joe Dirt is going down the highway. And if I say that Joe Dirt is traveling at 106 miles per hour, right? That's something you're familiar with. Maybe not this speed itself. I hope not. But you're familiar with this way of reckoning speed. First of all, we again didn't say Joe Dirt in reference to such and such is going 106 miles per hour. But without ever realizing it, we do that. And what is the implied frame of reference? The word implied means like, I didn't say it out loud, but it's understood to be true. What is the implied frame of reference here? We never said it, right? That's the whole point. That's why it's implied. What is the implied frame of reference? Compared to what? That's another way of asking it. Compared to what? Compared to what is Joe Dirt moving 106 miles per hour? Is Joe Dirt moving 106 miles per hour compared to this 18-wheeler that's in front of him going 36 miles per hour? Yeah. Compared to this, is he moving 106 miles per hour? No. So what? Compared to what is he moving 106 miles per hour? Okay, we're going to get there, but that's not quite right at this stage. 100. Well, compared to what? Compared to what object?
The 18-wheeler.
No. Compared to the 18-wheeler, he is moving 70 miles per hour. No. Okay, that's better. That's closer. I like that. The one option we have here is original point. Not usually, but that I like where you're going with that. What compared to what though? We don't have to know his original point to know this. There goes one right there. You see? That's Joe Dirt. He's only going 55 because that's the speed limit. Well, it's 50, but he's probably going 55. You know how it is. Compared to what? We saw it go by. We could see that blue pickup moving, that F-150. Did you guys see it go by? It doesn't matter. Just imagine if you didn't see it. Compared to what? How do we know from sitting in this room? Compared to what? There you go. That's what I'm looking for. The road. The road, I'm going to put that in quotes because it's not always a road, right? Like if I say that bird is moving 60 miles an hour, that's not compared to a road. The road, the grass, does it have to be the grass? No. What are we getting at when we say these things? We might even say us, right? I was kind of hoping one of you would say compared to the observer. But none of those is really true. We're comparing all of these are getting at what we usually compare linear motion, that is motion in a line. We're usually comparing it to what? All of these things involve what? What do we call all this as a group? All of this is part of something bigger. What?
The world?
There you go. That's it. The earth. That was a real stretch. We finally got there, Lizzie. Thank you. So compared to the earth is what our usual implied frame of reference is. If we don't say compared to the 18-wheeler in front of him, or compared to the flagpole, or compared to the clouds, if we don't say anything, we just say he's moving at 106 miles per hour, we're implying that that's compared to the surface of the earth. Okay? So that's something you should understand. So, and that's to say that even when we don't feel like we're using a reference point, even if you're not saying, well, relative to Mr. Kime's head, that marker was moving 2 miles an hour, even if you just say the marker moved 2 miles an hour, you are comparing it to the surface of the earth. Because most objects that we're used to dealing with are relatively stationary. They're mostly stationary. Right, let's look outside of the traffic again. Let's just watch traffic for a little while. You see that one? What is that, a Honda CR-V?
It's Irene.
Is it?
Yeah.
Okay.
It's an HRV.
HRV, sorry. Yes, Honda HRV. Did you see Irene go by in the HRV? Compared to what? Like you could tell she was moving. Oh yeah, there's the van.
It's a napper van.
A napper van.
Kids go to have long naps.
Yeah. You guys are saying the cutest little things. But how do you know they're moving? Compared to what? Like you don't even realize that you're doing that, but compared to what are they moving? Now that you can see, specifically the bridge or the highway or the grass or maybe that tree between us and them or maybe us ourselves. But all of that stuff, we're really comparing it to the surface of the earth. Okay? So that's the first thing, is that all motion depends on a reference point. Now draw your attention back over here. All motion depends on a reference point. All motion, we might say, is relative. All motion is relative. That means it must relate to something else. It must be in the context of something else. It must be spoken of in terms of something else. All motion is relative. Even if we don't realize that we're relating motion to something else, we are always relating motion to something else. We're always describing its reference point. And that's why if you imagine the marker moving in outer space, you wouldn't know whether, like, unless there were stars in the background or something, you wouldn't know if it were moving or not because there's nothing there to relate it to. We could, let's, not in the same spot, back to that, not in the same spot, how could we define motion in general? Give me a definition of motion in general. like Daxton said, not in the same spot. It's a change in what?
Speed.
Does it always have to be a change in speed?
Change in position.
There you go. Change in position. And I'm glad you remembered that, I hope, from your vocab. Change in position. This is no longer working, but that does remind me to do picture-in-picture. Is it picture-in-picture now? Okay. Change in position. So linear motion describes a change in position. Why linear? There it is. Motion in a line. Now, the two things I had you imagine were, how do I know it's moving? Right? And how would I measure that motion? How fast is it going, or how would I know it's moving? And how would I measure the speed at which it's going? Well, what do I need to measure its speed? Let's go down here. What is this, when we had Joe Dirt moving 106 miles per hour, or we had the 18-wheeler moving 36 miles per hour, how was that motion measured? There's a tool, and you can answer a speedometer. So Joe Dirt, in this little thing, would reckon his speed by looking at the speedometer. How does the speedometer work? I'm not asking for its mechanics, but what is it measuring? It's measuring speed in miles per hour. It's measuring, in a way, it's measuring what Joe has gone compared to what Joe has gone. Okay, there you go. How many miles? It's dividing that by how many? How long he's been driving, which we would measure in hours. That's where we get miles per hour. Just FYI, the word per in math is this division sign. So miles divided by hour. MPH, we would never write it like that in science. In science, we would write miles over hour, but miles divided by hour is miles per hour. And so we always have to have, when we're measuring motion, we always have, what kind of thing does miles measure? Distance. And we always divide it by, what kind of thing does hours measure? Time. And what do we get with that? Distance divided by time then equals, what do we call this? You know what this is called. Well, the whole thing. You know what it's called. It's, what? What are we measuring there? Speed, yeah. So speed equals distance divided by time. Doesn't matter what units we use. We're used to using miles per hour, but can you imagine something that we would measure as feet per second? Have you ever heard the measurement feet per second? Who has heard that? Paintballer. Or what? How do you know? Are you a paintballer? No? When have you heard feet per second? Okay, sure. Yeah, are you a paintballer? Sometimes. They measure the velocity of the paintball in feet per second. Real firearm, like a gun, right? That measures in feet per second. The muzzle velocity of a firearm, the velocity is a slightly different thing we will talk about. But speed is measured, we could measure in feet per second. Could we measure it as yards per minute? What could we measure in yards per minute? We could measure a very slow football player in yards per minute. Could we measure in yards per second? Yeah, faster football player we could measure. We could measure either slow or fast. We would just get more reasonable numbers if we use those different units. What about, you could pick any distance unit. What about centimeters per century? What's something we can measure in centimeters per, for one thing, the answer for all of these is everything. We could measure the speed of Irene and her HRV in centimeters per century. It would just be an enormous number, right? Because we can convert those just miles per hour to centimeters per century. But we could reasonably measure something like, you said a snail, maybe very, very, very long-lived snail, tortoise. I was thinking tectonic plates. You guys know about tectonic plates, that those move. We would measure that in very small distance units by very long time units would give us that. So, and also something moving very fast, faster even than a bullet, like an airplane, we could measure in miles per hour, certainly. But we could also measure it in something larger than miles. I don't know. You can measure it in, let's do a spaceship instead. You could measure a very fast spaceship in light years per century, for instance. Like a light year is a much farther distance of measurement, and a century is a longer time, but that maybe a spaceship could be measured in that way. So we always have a distance unit divided by a time unit, and that gives us speed. Now, what is the difference from your vocab between speed and velocity? We said muzzle velocity a second ago. What's the only difference between speed and velocity? Okay, I'll accept that. Yeah, trajectory. I like that. Because it must include what? Someone else. It's a speed with a... You remember it was in your vocab. A speed in a particular Not necessarily. Closer. Not quite. Did anyone do their vocab? Was it? Didn't you guys? Okay. That's speed to how fast the motion is. But velocity has to also include the objects. Help them, Miss Vogel. Speed with no, that's a different thing. Acceleration is a different thing. Speed in a particular. Did you guys do your vocab? That's an honest question because I thought I signed it. Didn't we check it? It was the day you were gone. Yeah, it was the day you were gone that I checked it. We'll deal with that in a second. Speed in a particular direction. I'll just tell you. It has to be in a particular direction. So we call it, back to the gun thing, we call it muzzle velocity. Does the direction the bullet is going matter for that? Yeah, it kind of does, right? If it was going towards you, that would be different, right? That would have a different effect than if it was going away from you, right? If you pull the trigger of the gun and it goes any random direction, that's not really what you want from a firearm. You want it in a specific direction. And so this is a speed. If we were saying Joe Dirt is going 106 miles per hour speed, if we were saying Joe Dirt is going 106 miles per hour south, that's a direction. If we say this semi-truck is moving 36 miles per hour left, that's a direction too. There are different kinds of ways of measuring directions. There's some are more precise than others, right? We could say on a Cartesian coordinate grid, the such and such thing is moving at 136 degrees south of west, if we want to be more precise. But usually we use these more basic measurements for direction. And then, finally, speaking of velocity, so that's a speed with a direction. If that velocity, I wish I had more room over here, but I don't, so I'm just going to start writing over here. If that velocity changes, velocity change, now what do we call that, Mason? That's the word you kept using that you were, what's that one? The change in velocity. Say it. Acceleration. There are three ways an object can accelerate. And because, remember, velocity is like speed, but it has direction. You tell me the three ways an object could accelerate. How could its speed or direction, right, because those things together make velocity, how could its speed or direction change, and any change in that is acceleration? So tell me the three ways it could accelerate. Give me one.
A hill.
Okay, so what's a hill making it do?
Going down. Hill.
Okay, so what is that? When you say go down, when maybe it was going what we would call flat, go down, what do we call that? It's changing its what? Okay, it's changing its velocity, but changing what part of velocity? Well, that's a different thing, right? He just said going down. It's changed its direction. Okay, so there's one. Change in direction. Change in direction. So going downhill is a change in direction. But it also usually, if you've ever ridden your bike down the hill in front of my house, Daxton, then you know that also usually, because of gravity, changes your speed. And there's a couple, what are the two ways that speed can change? So one way acceleration, change in velocity, can occur is change in direction. Two other ways. What are the two ways that speed can change? Slow down and speed up, right? All of those are kinds of acceleration. And that leads us to, there are two ways that an object is not accelerating. There are two states an object can be in where it's not accelerating. One's really easy. If an object's motion is not changing, it could be doing what? If an object's motion is not changing, it could be doing what? Sitting still. There we go. That's one. That's the easy one. And the trickier one is that it could be moving, right? It has to be a change in velocity. So moving, but how? Specifically. No, that would be, I mean, maybe, but relative to what? That would be a change in direction, though, right? How else could it not be accelerating? Moving, but specifically, it can't be changing its velocity. Nope, that would be slowing down, which is an acceleration. Okay, how could its how could its velocity stay the same if it is moving? Moving how? So it can't turn, so it must be in a straight line. And it can't be going faster or slower, so it must be at a, what would we call that? What kind of speed would that be? At a what kind of speed? Straight line and a oh no, I almost said it. Almost. What's the word? Constant. There we go. Phew. You got it, Gavin. So there are three ways an object can accelerate. If it changes direction, if it slows down, or if it speeds up. Those are all acceleration because its velocity is changing. And there are two situations in which an object is not accelerating. If it's sitting still, or if it's moving in a straight line at a constant speed. When do you move at a straight line at a constant speed? When on the highway do you move at a straight line at a constant speed? Yep, cruise control. There you go. So are you accelerating? Here's the way you can kind of tell. This will be the last thing. Here's the way you can kind of tell. You can feel acceleration with your body, right? If you don't drive probably, but your mom drives you around. And so even if you have your eyes closed and your AirPods in, can you feel if your mom hits the brakes?
Yes.
Yep, that's an acceleration. You feel that. Can you feel if your mom guns it to get away from the cops? Yep, because that's speeding up. Can you feel if your mom goes around this corner outside of Crawford?
Yes.
Even with your eyes closed, right? You aren't seeing the scenery go by. You're not seeing the change in reference point, but you can feel the acceleration. Now, if you're sitting still in the driveway, do you feel a change in motion? Of course not. But also, if you have the cruise set and you're going in a straight line, you also don't feel that because there's no acceleration. Does that kind of make sense? So change in velocity is called acceleration, and it can happen in these ways. It can also not happen in these ways. And remember that velocity is speed with direction, and we measure speed as distance divided by time. We always have a reference point for speed. Do you have questions about any of this? Okay. Bye.